It's wonderful to be here, and thank you for your warm welcome this morning. What I'd like to do is spend this morning talking to you a little bit about how technology is playing a major role in transforming the transportation industry. And I want to give you some insights into what we're doing at Nvidia and give you a sneak peek into some of the labs that we have around the world. And I think what we've seen, of course, over the last several years is a growth in computing across all industries. And the CPU, year after year after year, would just get faster and faster and faster, and everyone's code would just run faster. But what's happened over time is the end of Moore's law, and the laws of physics have basically prevented those normal gains from CPUs from occurring. And instead, what we've seen now is the growth of data in terms of the processing that's required, and especially in artificial intelligence, just keeps increasing. And this is at the time where the CPU has trailed off in its performance. And in fact, the GPU, the massively parallel cores of a GPU, have been able to open up new opportunities in artificial intelligence, machine learning, as well as then being able to use it in all kinds of different industries, from healthcare to energy exploration, even in retail. And what I want to focus on, of course, today is how we're using artificial intelligence for self-driving vehicles. Now, essentially, there's a whole new model of computing. And instead of engineers sitting down and writing code, the data is being used to write software. So we can train deep neural networks. We bring in massive amounts of information. We have inputs and outputs. There's all different types of neural networks being developed. But this is the new age of computer science, data science, and the data ultimately writing the code. And the more data we feed in, the better the code, the better the results. And it's an iterative process. So we're training in the data center and then creating these models. So essentially, what we're seeing now is all kinds of amazing software come out of this. There's one application that's just being used to colorize old black and white videos or images. And so we've trained it on black and white images, and so now it can colorize them. In the automotive space, we're actually taking segmented images, and we can generate photorealistic imagery from those segmented images, where there's just a couple of colors that are denoting the road or different objects. And then based on a lot of data that we've collected from real drives, we can generate synthetic imagery. In retail, in fashion, there's ways to, again, do pixel-level replacement here. So we have a video input, and the neural net has been trained on ways to recognize hair and can colorize the hair. This type of technique, again, is transfer learning that we can apply in all different ways. Even the art community is embracing it. Here's an application we call GOGAN, which is a generalized adversarial network. And we have different types of objects denoted by different colors. What's a rock? What's sky? What's ocean? And as the artist on the left is drawing something and filling something in as a rock or a cloud or whatever, the AI is creating the image. So we have the ability to take all different types of data inputs and generate different kinds of data outputs. Now, this is really interesting and beautiful here, but in reality, this is very different from what we're talking about in terms of the applications for self-driving, but the core fundamental techniques of taking data, being able to analyze it, recognize it, detect patterns, and then take actions is universal across machine learning. So essentially what we're doing is this training side. It's an iterative process where we take data in, we're able to then train our neural nets, we can test it, and we continue to iterate over and over. And then once we've developed that neural net model, we're able to put that into a device. Could be a phone, could be a cloud service, could be a vehicle. And so we have these different solutions that we've been working on for training and then for inferencing. So these are the two aspects of deep learning that we're working on. We believe that everything will be autonomous. Cars, trucks, buses, shuttles, all of these technologies that we're developing will be made available to the public through all these different means of transportation. Essentially, and this is kind of hard to read, but if you guys have seen this, it's pretty amazing in terms of the growth of what's happened in Silicon Valley. Virtually every car company, every tier one, suppliers, hardware companies, software companies, sensor companies, Tons of startups. There's hundreds and hundreds of companies in Silicon Valley now focused on self-driving. So what we've done is we figured this is such a complex problem. It requires so much work, so much partnership to do this. We've created a platform to handle all the types of computing and developed a lot of the hardware and software to then enable you all to build your products and solutions on. There's basically three aspects, though, of what we're doing in terms of this workflow, this end-to-end pipeline. First is the training. Needs to happen in the data center, requires a massive amount of compute. Of course, then it goes into the car. You need to have a supercomputer that's capable of taking all that sensor data in and figuring out what to do. How do you steer, brake, accelerate, and do it safely? But before we get to that point, there's really a missing phase that we've been investing heavily in, which is for testing and validation. And so simulating what happens in the real world is the way to get the miles needed to statistically show that what we're developing is much safer than any human driver. So let's take a look at, again, as we drive, we look around, we have our eyes, and we see the scenes, and then our brain figures it out. But as we're developing a self-driving car, we're going to take the human eventually out of that vehicle. And so we need an AI that is able to, again, sense the world, understand the lanes, the other cars, the trucks, pedestrians, trees, signs, the list goes on and on and on. And this is where it requires a massive amount of computing. To be able to do this, we're running many, many simultaneous neural networks in the car. A lane detection, a pedestrian detection, a sign detection. But it goes beyond that. There's different types of sensors, radar, LiDAR, cameras. And so different neural networks are processing different kinds of data, be able to localize using this information, identify where you are on the map, as well as then be able to anticipate how these different types of objects are moving and then anticipate their space in the future and plan a safe path around them. What we've done is we've introduced something called the DGX. This is our supercomputer that is being used now by the auto industry, among other industries, to train deep neural networks. It's specifically designed for AI and machine learning. We introduced the SuperPod, which is over 1,500 of our GPUs in racks and racks. It's about the size of a tennis court. This supercomputer is so powerful, it ranked number 22 on the world's top 500 at the International Supercomputing Conference. So this is what the industry is recognizing they need to be able to train these systems to be able to drive much better than a human. The problem is there's so many different things that can happen on the road. The complexity of the software developing is massive. What I wanted to show here is a kind of a sped up video of a car with 360-degree sensors. Now this is actual footage taken in Las Vegas and then superimposed in a CG environment, computer-generated environment, to show how the car actually sits in that environment. But what you can see is then there's full surround perception and massive amount of identification of all the pedestrians, other vehicles, and the signs. Now we can't drive around everywhere and expect to find all the potential problems that you would encounter on the road as the masses of us potentially see. Any one of us tends to not see anything that interesting on your daily drive. But as a world, there's a lot of accidents, injuries, and fatalities that can be prevented. So the key, we believe, is to augment test drives with virtual test drives. So the way to do this is to create a fleet of virtual cars in a virtual environment. We've introduced something called Constellation. So this is moving it into the cloud, putting a virtual car in a virtual environment. There's two servers here. One is full of GPUs, so it's generating virtual sensor data. The cameras, the radar, the LiDAR in this virtual environment are the output. And it goes into a second server that has the Nvidia drive system. So this is the actual hardware and software that will ultimately go into a self-driving vehicle. We're able to take those synthetic inputs and run the algorithms, run the detection algorithm, run the path planning, run the mapping, and determine how do we drive? Do we accelerate, brake, turn left, or turn right? And then we feed those controls back into the simulator. And then we do this 30 times a second. So this hardware in the loop is a way for us to evaluate everything in that car before we put it on the road. So what we can do is much, much safer than the real world. These two servers work together and we can generate front cameras, rear cameras, side cameras, and you can see then the environment, and it kind of starts to look like a video game. But what we're essentially doing is simulating the actual inputs into the system based on the environment. And so we can create all different kinds of scenes. We can create all different kinds of conditions to test it in, especially those kinds of rare situations that don't occur very often, a child running out in front of a car or somebody driving through a red light. So this tool enables us to actually build all kinds of environments. We can ingest the maps from all the HD mapping companies around the world. We can create all kinds of different scenes. We can bring the buildings in from land management databases. So again, it's leveraging the history of CAD and graphics, creating these virtual environments, adding realistic types of foliage, different signs, things you'd find in the road. And the whole point here is to build this environment that starts to mimic the real world. We want to be able to recognize everything, so we introduce all these different types of objects and things that you would actually encounter in the real world. Then the other aspect, of course, is what kind of sensors do you put on the car? So the simulator lets us build the vehicle, put different sensors on in different places. We can try different configurations of sensors, so we can determine what's the ideal configuration in terms of cameras, radar, LiDAR. It enables automakers, truck makers to experiment and see what is the most effective. And then what we can do is actually create scenarios, or we can import scenarios. This Constellation system is an open platform, so mapping companies, vehicle dynamics companies, traffic scenario companies can all ingest their information into Constellation, and now we're able to run this all at once, and we can then react in a virtual world and make sure that everything works fine. And then finally, we can test in all different kinds of weather conditions. So changing the lighting, the time of day, rain, snow, fog. And this becomes a really valuable tool to be able to assess the hardware and software that we've developed. Is it safe to put on our roads? This, again, replaces one of the test vehicles. Now, we're not saying to not use test vehicles. Obviously, you need to have test vehicles on the road. But before we get there, we want to be able to test 24/7, and we can do that in the cloud. And then we can scale up this into a massive data center where we have tens, hundreds, or thousands of these Constellation servers able to deliver all different kinds of tests and do it around the clock. So we've already announced that we're working with Toyota Motors, and we're working with Volvo to take this technology, bring it into the data center for training, testing, and then ultimately deployment. And what this enables us to do then is run all these tests, again, regress our software against known things, and also be able to create a whole new database of potential hazards that, again, would be too dangerous to test in the real world. So our focus is on safety, and this is one of the key areas to enable us to deliver safe self-driving cars. Now, as we go into the car, you need supercomputing there as well. Certainly not the same scale you need in the data center, but as the inputs come in from the cameras, the radar, the LiDAR, they need to run a lot of different algorithms. Now, the key here to safety is through redundancy and diversity. We want to have redundant sensors. We have redundancy built into the hardware of the car, but also diversity is key, because if there is an issue, we don't want to replicate that issue through redundancy, but through different types of sensors, through different types of algorithms, and different types of processors on this SoC, we can achieve that diversity and redundancy together. So on this chip, there's CPUs, there's GPUs, there's deep learning accelerators, there's video encoders and decoders, there's image signal processors, a massive amount of computing, 30 trillion operations per second on the chip the size of your thumbnail. And it's very, very energy efficient. So we pack all of this computing into a device that goes into the car. Now again, this is not a normal car. Essentially, there's a supercomputer on wheels, And it's running a lot of different software. And the focus of the future is a software-defined car. So a drive operating system, we have our drive AV, which is the autonomous vehicle layers for all the sensor processing, mapping, path planning, and then drive IX, which is the user interface. There's a whole other area of work going on to change how do we as humans interact with these machines as they become autonomous, using voice, using gesture, augmented reality. The interface is a big part of how we'll interact with these cars in the future. So this whole software stack is something that we make available to you to build your applications on top, whether they're cars, trucks, shuttles, or other types of vehicles. Now we pull this all together, and I want to close with a short video of what we've done now with one of our test vehicles out on the road in Silicon Valley. So there's a number of different freeways all around that map that I showed earlier. And you can see here, here's an 80-kilometer loop that we took our vehicle out on. And essentially, we do this on a regular basis. We have safety drivers in the car, of course. We're one of the licensed companies in California. But we use this to then test the algorithms after they've gone through simulation and learn from that and get more feedback and collect more data. So we're testing our Drive AV software. We're testing our Constellation software. Here you can see the simulation running side by side with the actual car. So we've mapped all the roads that we're driving on in simulation. And we can run different algorithms. We're doing the distance to other objects through camera-based. We're doing map localization through LiDAR. We're doing our lane detection, our sign detection, our weight net detection, our path planning. So many applications running simultaneous that are used to, again, create a safe self-driving experience. So the car can make its own lane changes. The car is able to then handle a whole host of different levels of autonomy. So whether we're talking about driver assistance systems or we're talking about fully autonomous robotaxis, this core platform and the hardware and software scales across it. We can do driver monitoring. Again, it's all the same. We have sensors faced on the driver as opposed to the outside. Here we're showing voice as well. A key part of the interaction will be through voice, a hybrid voice, so using artificial intelligence in the car to do the first level of voice processing. And then if we have to go out to the cloud, we can do that as well for searches or other types of services. So there's a massive amount of software development that we're still in the middle of developing. We're not there yet. There's still work to be done. But I think that's why we're here today, is to figure out how we can better work together. Being a Silicon Valley company, we have presence all over the globe in all the automotive hubs, whether it's in Japan, whether it's in Germany, in Detroit, but also here in Seoul. Part of this video then is lane changes, freeway on-ramps, off-ramps. And this is kind of the first phase of how we're bringing this to market in controlled environments. On the highways, maybe in geo-fenced areas, in the ports, at airports, on college campuses. So we're going to see a lot of work coming to market soon in terms of shuttles, and then eventually into private ownership of vehicles. As I mentioned, we're working with a lot of different companies. Over 450 companies are using the Drive platform, and many of you in the audience, I know, are part of our ecosystem. So whether it's a car company, a truck company, a sensor company, tier one, mobility services, software companies, we've developed this product for you, and we want you to be able to use it. So I'll be here the rest of the day. If some of you would like more information, please feel free to seek me out. And I want to thank you for your kind attention. Appreciate it.